Okay, so maybe we get started. The main goal of the talk is to, apart from getting to lunch on time, is to kind of summarize where we stand with respect to positive techniques and then introduce lower bounds again. So we had a brief introduction to a mysterious set of problems that we said were as hard as solving the clique problem. But we gave no serious intuition for why we should be so afraid of clique. So today we will still be a little bit vague because nobody really understands these things very well, but we will try to build up to, assuming certain other things which are a little more reasonable, we will try to give you some intuition about why clique is expected to not have a FPT algorithm. Okay, so just to recap, typically the main issue is that you have a parameterized problem that you would like to solve, and you have one of two situations. Okay, the first sanity check you want to do is what is the status of the problem for constant values of the parameter. Okay, just if you're starting off with an unfamiliar problem and you're totally clueless, of course you typically be starting with an NP hard problem, but you try to examine what the problem is like for even constant values of the parameter. For problems like satisfiability parameterized by the length of the longest clause, or chromatic number parameterized by the number of colors, you would immediately conclude that even for constant values of the chosen parameter, the problem is NP hard, and therefore you don't really expect to have a f of k poly n algorithm, because that would contradict the hypothesis that p not equal to NP. On the other hand, if you find that for constant values of the parameter you're sort of doing okay, then there is hope that perhaps, well, in this case, what is the situation? Typically, easy meaning you have an n to the k algorithm, for which would mean that for constant values of k, this is a polynomial time algorithm. Okay, so that's an algorithm that's easy to come up with for several problems, especially subset like problems. Just if you're looking for a subset of size at most k which has some property, typically if the property is verifiable in polynomial time, typically just brute force over all subsets of size at most k gives you a trivial n to the k algorithm. So that's our more usual starting point. And here one of two things might happen. Either you can apply the vast toolkit that you have been introduced to so far for coming up with FPT algorithms and actually get an algorithm of this form, or you use the reductions that you saw maybe in the second lecture on the second day and conclude that the problem is as hard as clique, whatever that means. And that's what we are going to explore a little bit more in this lecture. On the other hand, in the next lecture, we are going to break this down even further to talk about kernels. So when do you have polynomial sized kernels is also a very natural question, because one of the first things that we saw when we did kernelization in the basic kernelization lecture, we ended with a theorem which said that a problem is FPT if and only if it has a kernel. But the size of that kernel is proportional to the FPT running time, so a natural question is when does the problem have a kernel whose size is polynomial? Okay. So as it turns out, with the advanced kernelization lectures, we've seen several examples of problems that do have polynomial kernels, but in the next lecture for the first time we will explore the theme of problems where we don't expect a polynomial sized kernel, and that's an entirely different flavor in terms of lower bounds machinery. So that's what's coming up post lunch and for several more lectures, but right now we are going to explore this a little bit more. Okay. So let's first define the notion of a complexity class in terms of a problem. Okay, so so this is just how I'm going to define a complexity class starting from a particular problem x. I'm going to say the guys who get a ticket to being in this class along with x are the guys that can be solved if x can be solved. So if there's a legitimate reduction from these problems, oops, went slightly ahead, sorry. So the problems that belong to the class defined by the problem x are all those problems that can be reduced to x. So these are problems that get solved if x gets solved in whatever time. So if you're talking about FPT, for example, the idea is that if this guy has a FPT algorithm, then these guys have FPT algorithms because there's a FPT reduction going from the blue guys to the big guy. Okay. So these are the guys that are allowed to belong to the same class as x. Now the green fellow is your problem. And if you have a problem for which you want to show that it belongs to a certain complexity class, then what you would have to do is reduce it to the problem that defines the class. Okay? Or more generally, you would have to reduce it to a problem that's hard for that class, which we define as being a problem for which every problem in the class reduces to. Okay? So these are just definitions at this point that we will keep using time and again. So just want to make sure that this is clear. For a given complexity class is just a collection of problems, typically decision problems with yes, no answers, and in our setting, decision problems with parameters that have yes, no answers. Now, a problem is hard for the class if every problem in the class reduces to it. And so if you want to say that your problem belongs to a certain class, you just have to reduce it to a hard problem. Okay? Then you get your ticket of entry into the class. But what if you're a little more ambitious and you want to say that your problem is actually hard for the class? Okay? In that case, you would actually have to make sure that every problem actually reduces to your problem. Okay? Now, do you necessarily have to do this from scratch? It seems like a lot of work to go to every problem and say, hey, dude, please, can you reduce to me? So it seems like an incredible amount of work to show that your problem is a hard problem. It seems easier to show membership. So what would you do? What's an easier way of showing hardness? Right, reduce a hard problem to your problem. Okay? So you start off by defining a class with a problem that's hard by definition. Okay? So you already have at least one hard problem to begin with, and then you can slowly expand the set of hard problems by simply reducing a hard problem to your problem. Okay? Why does this work? Just because of transitivity of reductions. Okay? So if you have a FPT reduction from some problem A to a problem B, and you have a reduction from B to C, then you also have a reduction from A to C. That's quite easy to check. Okay? All right. Fine. So here's a problem that's a good candidate for being the starting problem for defining our class. Okay? I'm going to say, so this is the analog of the Turing machine acceptance question in the classical setting. Okay, and I'm going to use this problem. Well, I'm not really going to use this problem, but well, let's just play around with this and see where we go. So let's begin by defining the problem. So you're given a non-deterministic Turing machine. Guessing everyone's seen this before. There's a tape with symbols written on some cells of the tape. There is a head and there is a state. Okay? And the head moves around on the tape. It reads the symbol, it looks at the state that it was in, and depending on the transition table, depending on what the transition table asks it to do, it either changes state or remains in the same state. Okay? So it keeps doing this. It can also write to the tape, it can change the symbol that was written to the tape, and in every transition of the Turing machine, the head moves either one step to the left or one step to the right, and it can change the symbol that the head was seeing in that particular step. Okay? And among all the states that the Turing machine can be in, some states are declared to be final states or accepting states. So if after the Turing machine does whatever it has to do, if there exists a computation path that takes you to an accepting state, then the Turing machine is set to accept the input. Okay? It's a bit of a mouthful, but I guess all of you have seen Turing machines before, so hopefully this is okay. All right. What's the short Turing machine acceptance problem? You're given a non-deterministic Turing machine and an input and an integer k, which is the new part. And the question is, does the Turing machine accept the input in at most k steps? Okay. And k is, no surprises for guessing, your parameter in this problem. Okay. So the question is, you're given a non-deterministic Turing machine, you're given the description in terms of the transition table, and the question, and you're given a candidate input, and you want to know, does this guy accept it at most k steps? Okay, now let's go to a familiar region, which is the independence set problem. And let's say that if your complexity class was defined by the short Turing machine acceptance problem, then the independence set problem belongs to the same class. For this, we have to show that independence set reduces to short Turing machine acceptance. Is that clear? Right, right. That's the definition of the problem. That's what you're given as input. Yeah? Okay. Fine.
reduction is supposed to be how much time?
It's a FPT reduction, it's the usual. It's a FPT reduction.
Is it because we know that the short Turing machine acceptance can be done in FPT?
No. We don't know anything about anything in these matters. All I'm saying is abstractly, let's define a class. Let's call this class something, I don't care. I mean, I don't want to give it, okay, let's call it W1 because that's what it is. So let's give it a random name. Now let's say that I define this complexity class as being the set of all problems that can reduce to short non-deterministic Turing machine acceptance. Okay. Now right now, this guy is definitely here because it self-reduces trivially. Okay, so short non-deterministic Turing machine acceptance just is the defining problem for the class. So it's definitely in the class. Now, can I find another problem that belongs to the class? I'm claiming that independent set is such a problem.
This reduction has to be in the time proportional to the time that it takes to solve that problem.
So no. So in the context of what we are doing, the reductions are all going to be FPT reductions for the following reason. If you have FPT reductions, then the kind of statement you can make is that if there exists a FPT algorithm for, let's say, short non-deterministic Turing machine acceptance, then independent set is also FPT. Okay? This is your typical if-then kind of statement. That's the sort of thing we were saying the other day. If you can solve clique in FPT time, then you can solve whatever in FPT time. And okay, the intuition is that you don't really expect to solve short non-deterministic Turing machine acceptance in f of k poly n time. The reason being, okay, what would you have to do to solve the problem in whatever amount of time? You have a question? Now, right now, I just want to show that independent set belongs to the same class as this guy. I'm not trying to say that he's as hard as this guy, not yet. I just want to say that he's in the same class, meaning that, so what happens if I put independent set in the same class as the STMA problem? Okay, this is legitimate if there is a reduction from independent set to here. Okay, independent set is itself hard for the class if you have a reduction this way, which we will come to next. Okay, but before it can be, I mean, of course, you can be hard for a class without belonging to the class, but I'm wanting to say that independent set is very much a part of this class. It belongs here and it's hard for the class. Okay, so there are two issues. One is membership and one is hardness. For membership, you have to reduce to a hard problem. For hardness, you have to reduce from a hard problem. Clear? Okay, and the intuition is that the reason we are trying to start from this guy is that, okay, so what's the point of saying that a bunch of problems reduce to and from STMA and that they're hard for this class that we define? All these hard problems we don't expect to be in FPT, because if you think about it, okay, so a short Turing machine acceptance problem can be solved by simulation, essentially. You can take your Turing machine description and you can try to simulate what it will do in k non-deterministic steps. But the issue is that these steps are non-deterministic. Okay, so in every step you would have to you would have to branch into something like order n branches. Okay, because in the first move, it can do order n many things. It can write there are order n possibilities of what symbols it can write to the tape. Then there are two possibilities, left and right. There's something like order n possibilities of states that it can move into. So there are a hell lot of things that it can do in the first step. And you would have to exhaustively branch on all these possibilities. So that's your first branch. Then the second branch. Of course, the depth of branching is bounded because you still have only k steps to do your business. But the branching factor is huge. It's order n. So the easy algorithm is n to the k. Do we expect to be smart and to be able to reduce this to f of k poly n? Well, nobody really has a good answer for this, because this would mean showing a lower bound that doesn't depend on anything, which is a problem that we always deal with. But the intuition is that a Turing machine is a very powerful adversary. As a problem, it's a very opaque object. Okay, it's about as generic gets as far as problem descriptions go. So if you try to be smart and if you try to save on the exhaustive branching, chances are that somebody will be able to come up with a Turing machine that defies your algorithm. Okay, that's the kind of, I mean, because this is about as abstract a definition of a problem as it gets, the expectation is that the exhaustive approach is the only approach. Okay? That n to the k is where you're going to be stuck if this is the problem you're dealing with. Okay? It's the same intuition that drives P versus NP, right? Because you're thinking of the classical question in NP that has a polynomial certificate is just Turing machine acceptance, but you don't expect to. And Cook's theorem tells you that SAT is as hard as doing Turing machine acceptance. You start with an instance of a Turing machine and you reduce it to a big formula or a big circuit or whatever it is, and then you have this whole snowballing of problems that are NP complete. Okay? So it's the same kind of intuition here as well, except that since we are talking about parameterized problems, the k needs to come in somewhere, so the natural analog is the number of steps. Correct, that's right. So you can restrict your attention to the first k cells. So that's fine. You can stop at the first k cells, but the number of configurations, right? What is it that is written on the cells, and what are the potential states that the machine goes to? You can have a lot of junk written on the cells, right? And that's a part of the input, and that's order n. Yes, you can, and that's why the depth of branching is bounded. You're right. I mean, you can only go up to k cells at the max, probably even less if you're going back and forth. But what you write on the cells and the states that you can move across, they are unbounded. I mean, unbounded in terms of k, bounded only as n. Okay? So I hope that makes sense. And the fact that this guy is such an opaque object means that we don't really hope to pierce into it and improve this to something like f of k poly n. So that's the intuition, and let's see why independent set resides in the same class as short Turing machine acceptance. This is just like an exercise in going through encoding. So sorry, I'm one slide behind. Okay. So with this sort of a reduction, we are given an instance of independent set as input. Okay, that's a graph and a number k, and you want to know if there are k vertices that induce an edgeless subgraph. Okay, what you want to do is come up with a Turing machine. Come up with a Turing machine which halts in an accepting state after some function of k steps, if and only if the graph has an independent set of size k. Okay, so any suggestions? Okay, so this is a non-deterministic Turing machine. Okay, so it can do a lot of guessing. Yeah, guess what? Guess the independent set, right? Guess the independent set and put it down on the tape. Okay, and then the Turing machine only has to run through the vertices of the independent set and make sure that they're pairwise independent. Okay, but the running through and the checking is encoded in the state space of the Turing machine. Okay, the Turing machine, I mean, this is something that was throwing me off a bit when I was reading this. The Turing machine cannot afford to move back and forth on the tape to go and check, to go and probe the adjacency matrix and come back and shift states and so forth. So the notion of whether it's reading an independent set or not has to be encoded in the state space. So just for completeness, let's go over this informally though. So let's say that my states are going to look like for every vertex A in the graph, and I'm going to have a state Q A comma happy. The happy is not really essential, but it's there for clarity. So as long as the Turing machine is in one of these kinds of states, it's going to keep going. Okay, the moment it becomes sad, it stops. That's a non-accepting state. Okay, so for every vertex in the graph, you have a corresponding state, and what do you do? So let's say you're moving along the tape, and so this basically tells me that I'm checking that A, the vertex A that I'm currently reading, is non-adjacent to everybody else that's written down on the tape. Okay, so I have The picture would be that here's the tape, and I have k candidate vertices written down on it. These are the guessed vertices. These are your non-deterministic steps. After this, it's all going to be completely determined. So I have a bunch of vertices. The Turing machine is going to start here, and it's going to say, okay, I picked up the vertex A. Now I'm going to run through the tape and make sure that A is independent. A is not adjacent to any of the other guys. So if it sees at some point a symbol B, and if the graph happens to have an edge between A and B, then the transition table will say move from the state happy to the state quit. Okay, that's when you spot an edge. If you don't spot an edge, then you just keep moving along to the right. Okay, when you encounter an end symbol, that means you're done with reading the list of vertices with respect to A. So you just start coming back on the tape. Okay, so that's a move state. Keep moving to the left, but the moment you move to the left and you come back and see A, take one step to the right, read the next symbol, grab that symbol, and work with that to make sure that that is independent of everybody. Okay, so you just have to do a number of steps back and forth on the tape, and something like k times k minus 1 or 2 times k times k. I mean, roughly order k square steps is what you need to verify that all of these guys are mutually independent. Sorry? Sure. I mean, now I'm showing that I can manage. If somebody gives me an algorithm for short Turing machine acceptance, I can use such an algorithm to solve my independent set problem just as easily. Right. Right. So the k is like a part of the input, right? It's a parameter. So I'm going to fix. Yeah, so I'm going to fix. I mean, the parameter is restricted to being a function of the parameter alone. That's the non-deterministic part. So there are k steps in the beginning which are non-deterministic. No. Yeah, exactly. The n-par k branches, but the number of steps, like in a particular run of the Turing machine, right? You're only going to spend k steps. Exactly. The important thing to notice is that I'm using the state space to verify that what I've written down on the tape is independent. Sure, I mean, my alphabet size is n times m times something. The states are helping me decide whether what I've written down on the tape is an independent set or not. Sorry? Correct, but I don't want the number of steps I have to spend, it has to be a pure function of k. No. Oh, no. But I don't have to, I'm not stuck with a unary alphabet, right? My alphabet, my symbol space can be big. No, but I'm not stuck with binary. It's not a binary alphabet, it's an alphabet of size n. And that is why you need n to the k time to solve the problem, because your space of. But why would you need log n if you have n distinct symbols? That's just, every symbol takes up one cell, that's it. Right? You are working over an alphabet sigma union some empty cell alphabet, right? Or you have a special symbol to indicate end of tape, okay? And sigma can be anything, it doesn't have to be binary at all. No. It has to be finite. It in fact has to be f of k poly n, but yeah.
So the definition changes.
The definition of what changes?
Okay. So in the general non-deterministic machine,
Right.
the number of state has to be constant. It's finite, independent of input length.
Right, but given a particular instance, I'm generating a fixed space of states. This is independent of input. What is the input?
exists a Turing machine?
It's a family of Turing machines. So like any
Yeah. I mean, for a fixed input, you generate a fixed Turing machine.
This is a Turing machine that these states.
You can also create it. There's no problem with creating it. What is the description of a Turing machine? You can describe a Turing machine completely by describing the transition table, right? And this is the transition table. These are the transitions. What's the confusion is not clear. That's not clear to me either.
So for the same Turing machine, if we give a bigger graph, then we won't be able to answer.
No. The Turing machine depends on the graph. For a given graph, you generate a particular Turing machine. Correct. I mean, I'm allowed to generate a Turing machine, right? The input to the short Turing machine acceptance problem is a Turing machine. So I'm allowed to create a Turing machine. And what is the input to this Turing machine? It's just the empty string. Okay? The Turing machine does its business. I mean, it has no input, right? Okay? All right, so given a graph, you generate a Turing machine that's fine-tuned to that graph, okay? And it has no input written on the tape. It starts in a happy state, and it's obliged to do some things, okay? It has to guess k symbols, write them on the tape, and then it has to move around in this very specific predetermined fashion. And somewhere along the line, it may shift from a happy state and go to the quitting state, or it may just survive all the way. And it's easy to see that if you start with a graph that has an independent set, there is an accepting computation path. At the point where you would have made the correct non-deterministic guess, all of these steps will never push it to quit, okay? All right, so I mean, you can verify that this actually works, but a more interesting exercise would be to check if this works for dominating set. Can you do something similar for dominating set? What would be an analogous construction? So again, you can start off by guessing the k elements that belong to the dominating set. Right. Now it's a little bit trickier because you're not checking a property of the set itself. You have to go out and make sure that the guys who are outside are actually taken care of by these guys, and try writing down the state space in time that's, try getting a state space that's f of k poly n, okay? It's a good exercise to play with it because it doesn't work out. Okay. Correct. But this is, okay, so in the parameterized setting, there is a difference between having a single tape and multi-tapes. But you're right, if you have multiple tapes, you can do something. And that's why the class of dominating set is characterized by multi-tape Turing machines and not single tape Turing machines, okay? But it's a slightly different class. It's the point that I want to make. So in any case, we'll come back to making the distinction between independent set and dominating set clearer, at least at an intuitive level, in a few minutes. But let's get back to the global picture. So I've defined some class, okay, in terms of the short Turing machine acceptance problem, and we believe that problems that are hard for this class are hard for getting FPT algorithms because this is just such a mysterious problem, okay. So what we have shown so far is just that independent set belongs to this class by reducing it to this guy, okay. But what we really want is to say that independent set is hard for this class, because then we have a nice natural problem that's hard from where we can do our usual business of reductions, where it's a pain to reduce from short Turing machine acceptance. And just to make that point, it's a pain to reduce independent set from short Turing machine acceptance, so we're not going to go into the proof. But okay, we will maybe see a rough outline of it in just a bit. Okay, so notice that all we have to do is reduce. So this was just a recall that you have to show that independent set is hard, you have to reduce short Turing machine acceptance to it, okay, which was the point that I think some of you were making, that why are we not reducing Turing machine acceptance to this guy? We'll have to do that now. If you want to show that independent set is hard for this class, this is what we'll have to do, okay. And okay, I'm actually going to demonstrate that it's a bit of a pain. So we will not go into a complete proof, but we'll see just a rough outline. So the input is a short Turing machine acceptance instance. So it's this big transition table, and it's some input string x, okay. What you'd have to try and do is, so every configuration, so we're going to use this observation that a few of you made, that in any accepting run, or yeah, in any legitimate run of the Turing machine, you will only be able to explore at the most the first k cells, okay? Because you're supposed to do whatever you need to do in at most k steps. So the number of cells that you can actually visit is at most k. So you might as well restrict your attention to the first k cells. And for each possible configuration of the Turing machine, meaning a possible location of the head, a possible symbol on the tape, or a possible sequence of symbols on the tape, and a particular state that the Turing machine is in, you are going to introduce vertices. Okay? You're going to introduce vertices that are going to go into your graphs. So in particular, to encode the fact that at step I, the head is at location j and the transition is delta. So delta is going to encode the current state, it's going to encode the symbol that's being read, and it's also going to encode what it's going to do next, what it's going to write to the tape, whether it's going to move to the left or to the right, and what state it's going to go into next. Okay? All of that information is in delta. For each possible combination of ij and delta, you're going to have a vertex. Similarly, you're going to have a vertex for saying that at step I, the symbol at a particular location is something, and the head is not at that symbol. So these are the vertices that are going to describe the rest of the tape. Okay? So you have a bunch of vertices that are going to talk about what's going on where the head is, and you have a bunch of vertices that are going to talk about what the rest of the tape is looking like. Okay? So in particular, these are the first set of vertices. So for every choice of delta, and so we'll just focus on what's going on at step 3, for instance. So on step 3, position 1, 2, 3, and so on up to k, for each of these guys, you're encoding what's going on at the head. Okay? And so for each of these guys, for all possible delta, you have these vertices. Okay? And then you have more vertices for saying what's going on at step 3 at the other positions. Okay? Now, how does independent set even begin to play a role? First of all, the independent set, so you can do multicolored independent set, it's slightly easier, and we have seen in the last class or the last lecture that multicolored independent set and independent set are completely equivalent. You can go back and forth. So you can use multicolored independent set to box in some of these guys to say that you must pick exactly one vertex in your solution from this set of vertices. Okay? So in particular, I can insist that from around here, you should pick exactly one vertex to denote where the head is, because the head of a Turing machine, even if it's non-deterministic, cannot be at two places at the same time. Okay? So you have to pick, let's say, exactly one vertex from here. Once the independent set does that, it's constricted to not pick anything from here, because this says that the head is not at this position. Okay? So you need to make sure that you have the right edges going across to say that if you pick this, then you don't pick anything from there. Okay? This you can do with a complete connection or whatever. So if you pick something from here, you don't pick anything from there. Okay? But you must pick something from here, and you must pick something from here to say what's going on. Okay? And you must pick exactly one thing from each of these places, because at every position of the tape, you have exactly one symbol. Okay? And you need to do a lot of careful gadgeting to ensure that you preserve the transitions correctly. Okay? That if you pick a particular choice for, this was just step 3, you're going to have another set of vertices like this for step 4. And if you pick some choice of vertices for step 3, the choice of vertices that you pick in step 4 must represent a legitimate transition from step 3 to step 4. So you use the transition table to add the edges correctly, so that if you don't respect the transition table, then you have an edge somewhere. Okay? So it's not an entirely trivial reduction, but imagine for every problem that you deal with in your day-to-day life, having to do a reduction from this guy. It's okay, it's conceptually not very difficult, okay? And the intuition is that the independent set size is bounded as a pure function of k, because the number of steps you're allowed to take is just k, okay? So that's the translation of the parameter, okay? And conceptually, you just have to encode a legitimate sequence of transitions, okay? And of course, you'll have to, keep some specific vertices to say that, what goes into the final state, and you have to delete some vertices to ensure that you don't start anywhere except for the start state, and all kinds of boundary conditions. So there's a lot of detail which is not irrelevant, but it's probably not worth getting into. So this is just the high level idea of the reduction. Okay. Let's move on to a different model of computation. This is going to be about a little bit about circuits. The reason we are going to talk about circuits is because here the difference between independent set and dominating set is a little more in your face. Okay, like you pointed out, in the Turing machine scenario, the difference really comes from having one tape versus multiple tapes. But in terms of circuits, it's a little more transparent. So it's first of all, everybody knows what a circuit is. You have a bunch of input gates, okay, and then you have AND gates and OR gates and NOT gates that are allowed to play around with the input gates, leading all the way up to an output gate. The circuit naturally reflects a computation. Formally, it's a DAG, where the input gates have in degree 0, and every other gate has in degree 2 or 1, depending on whether it's an OR gate, an AND gate, or a NOT gate. And then the output gate can have the output gate is one of these gates. It's just a particularly labeled vertex saying that, hey, this guy is the output gate. And the underlying graph structure, I mean, it's a directed acyclic graph. Okay, for those of you who like formalisms, yes. But I have not written all of this down. Hopefully everybody knows what a circuit is. Okay, what is the circuit satisfiability question? We are going to actually deal with a weighted circuit satisfiability question, again, because a k has to come somewhere in the picture, so that's going to come from the weights. Ordinary circuit satisfiability is that if you feed in specific values to the input, I mean, is it possible to instantiate the input in such a way that the output gate computation goes to a 1, okay? Assuming you're dealing with Boolean variables out here, can you assign 0, 1 values to the input gates so that the computation leads you to a 1 at the end of the day? Okay, the weighted circuit satisfiability question is very similar, except that you want to set exactly k of the input gates to 1. Okay, and the parameter is, again, no points for guessing, k. All right, so that's the question that we're going to deal with. Let's see why independent set reduces to weighted circuit satisfiability. This is again to get membership. Okay, so let's say now the defining problem somehow is going to be circuit sat. And let's just see why independent set reduces to weighted circuit set. So we have to come up with a circuit, right? So you're given a graph and we have to come up with a circuit. So maybe let's just start putting down the input gates and the output gate. Okay, this we need at the very least. And it's kind of natural to have one input gate for every vertex. Because what's the independent set question? It's saying, can you pick k variables, k vertices that are mutually non-adjacent? So picking k vertices somehow corresponds to setting k input gates to 1. Okay, so that seems like a natural connection to make. Now, if you have an edge between two variables, two vertices, what do you want to do to the corresponding input gates? You somehow want to lead it to an output that's negative, right? In the sense that if you set t and h, the input gates corresponding to two vertices that were adjacent in the graph, if you set both of those guys to 0, both of those guys to 1, sorry, then that signifies picking these two guys in your independent set when you're going in the reverse, okay? And this you don't want. So you want the output gate to sort of give be 0 if you set these two guys to 1.
So these two had an edge? They didn't have an edge.
So T and H have a graph, T and H have an edge in the graph.
So if they have an edge,
I'm saying that if they have an edge and if you set both of them to 1, then you want the output gate to be 0.
Then that is technically not AND, right?
Yeah.
AND and then
Yeah. NAND. You need a NOT. Okay, so negate the variables, and then do an AND. That's what you need. You don't set two input gates corresponding to an edge to 1 at the same time. If you set both of them to 1, they get negated, they both become 0, they pass through an AND gate, which is again 0.
But then even if one of them is 0, I think
Even if, no, I mean the AND gate is specific to these guys. I don't have a global AND gate or anything. I mean, no.
Yeah.
Right. Okay. Make the and or. Right. Yeah, I forgot to flip that. Sorry. Sure. You make the and or. Yeah. So so you negate these guys so that the semantics are flipped, and then you have an OR gate. So the demand is that both of these guys definitely cannot be set to 1. If both of these guys are set to 1, then the output gate becomes 0. What's the output gate, by the way? It receives all of these guys. Maybe let's draw the full picture. So you negate all the variables, and you have for every edge, you have a personal OR gate standing up for that edge and saying that I will not allow this edge to be picked. Okay, because if the variables, if the input gates corresponding to the edge are both set to 1, they both get negated, they both become 0, and then they come to the OR gate, they become 0, and this guy is a what gate? This guy is an AND gate, because every edge has to meet the constraint. Okay, so every edge has to meet the constraint that it's not violated. Okay, so you have vertices as input gates, they are negated, edges as OR gates, sorry about that, and the output gate is an AND gate. Okay, so if you have, formally, if you have an independent set, you just set the input gates corresponding to the independent set to 1, and you set everything else to 0, and all of these edges will actually survive because no edge was actually picked. So at least one of these guys would be 0. In the negation, at least one of them would be 1, and therefore the OR gate would push down a 1, and this guy is getting a 1 from everywhere, so it outputs 1. In the reverse, if you had an assignment with exactly k input gates set to 1, then I claim that the vertices corresponding to these gates must form an independent set. And suppose not, then there is an edge, and you work out the same argument. Okay, there is an edge, there is an OR gate corresponding to an edge, which must be getting a 0 and a 0, but that's getting fed into an AND gate, so the AND gate must be 0, which is a contradiction. Is that clear? Okay, so independent set reduces to weighted circuit satisfiability. Let's do dominating set. Okay, for a dominating set, again, I start with, for the same reason, I start with input gates as vertices, as representing vertices. So again, hopefully the input gates that are fixed at 1 will somehow correspond to my dominating set. Okay, so this is an output gate, and here I'm going to have, so in dominating set, what's my constraint? The constraint is that for every vertex, at least somebody in the closed neighborhood of the vertex is chosen, right? Here's what I'm trying to encode for all V. This is dominating set. So I have a constraint for every vertex, so I'm going to put down another layer of gates corresponding to vertices, which will hopefully encode my constraints. Okay, so for a gate here corresponding to a vertex, what must I do? Right, so I'll make it adjacent to all the neighbors, including itself on top. Okay, at least one of these guys have to be set to 1 for this gate to pass a 1 value below. Okay, and therefore if you have an AND gate here, all the constraints must be satisfied. Okay, and by a very similar reasoning as before, you can formally work out that dominating set translates to a solution, vice versa. Okay, is this clear to everybody? Okay, good. Correct. So both of them seem to be reducing to weighted circuit satisfiability, which seems to be a common problem. So we will make a finer distinction in just a minute, I think. Okay, sorry. Okay, so here's the situation with respect to independent set. If you have weighted circuit satisfiability as the problem, then membership is clear from what we have done. To show hardness, what will we have to do? Reduce the other way. Reduce weighted circuit satisfiability to independent set. And this is seriously messy. Okay, So at least the short non-deterministic Turing machine acceptance proof you will find in the book, in the notes that are there on the website, and you can go back to. This, the book says, is out of scope. Okay, it's probably there somewhere. I think in a series of papers by Downey Fellows going back to early 90s, also probably in the Downey Fellows book, but it's messy. I mean, I sincerely tried giving the high level intuition, but I'm not going to get into this. But it turns out that you can reduce weighted circuit satisfiability to independent set, which makes it hard for this class. But let's try and understand what's going on between independent set and dominating set. Okay, so just go back. Okay, I'd like to go back and have you stare at the circuits, but before that, let's just define this notion. Let's have this at the back of our mind. We call the Weft of a circuit. So let's say that, okay, so I want to distinguish the style of circuits that we used when we reduced from independent set and dominating set to the WCS problem. Okay, so in a circuit, let's say that you're trying to take a walk from one of the input nodes to the output node. On your way, you encounter some intermediate gates. Let's say that a gate is large if it sees a lot of things from top. Okay, in particular, if it sees more than 2 things coming in from top, I mean, if it has integrity more than 2, let's say that you have a large node. Okay. And so when you're taking this walk from an input node to the output node, let's say that the Weft is the maximum number of large nodes that you can possibly encounter when you take such a walk. Okay, so let's go back to the independent set circuit. What is the Weft of this circuit? It's 1, because there's only one large node in this circuit, which is in fact the output gate. Okay. What about dominating set? What's the Weft of this circuit?
2.
It's 2. Okay, so these are, in some sense, these are 2 different classes of circuits that we are dealing with. So let's define the following class: weighted circuit satisfiability as a problem restricted to circuits that have Weft 1. Okay, as it turns out, independent set, clique, and a whole bunch of problems that reduce from these guys are all hard for this class. Okay.
Any number of inputs can be reduced to 2 inputs.
And
adding more and more gates.
Any number of inputs can be reduced to 2 inputs. You mean the degree? Now it is true that you can go back and forth between. I mean that the fixed constant 2 is not important. Okay, but making the distinction between 2 and more than 2, I think, is important. So let's see why that's the case. Okay, let's say that the depth is fixed at a constant. Okay, I forgot to mention this because I wanted to keep the slide simple. Okay, so I think it's important that you're looking at circuits of depth for some fixed d. Okay, so if you try to do this reduction, the depth is potentially proportional to the input, which is not allowed. Okay. Now I'm just defining a class of circuits which have the structural property that they have Weft d and depth d for some fixed constants d and d. Okay, and we're just going to focus on. So let's restrict ourselves to the weighted circuit satisfiability problem, restricted to circuits that have Weft 1 and have some constant depth. Okay. Yeah, here 2 is enough. For this problem, 2 is enough. So for independent set, the depth is 2 or 3, depending on how you want to define the depth. Yeah, correct. So thanks. All right. So that's finally the class W1. Okay, W1 is the class of all parametrized problems that reduce to the weighted circuit sat problem, where the classes of circuits that we are restricting ourselves to are circuits of Weft 1 and some constant depth d. Okay. W2. No, D is fixed. D is some, it's a pure constant. Okay. W2 is similarly weighted circuit SAT. I mean, the defining problem for W2 is the weighted circuit SAT problem, where you're looking at circuits that have Weft 2 and some constant depth D. Okay. It turns out that dominating set and set cover and hitting set and a whole class of problems, well, they clearly belong because we just showed a reduction which way? We just showed a reduction from these guys to these guys. Okay, so we showed a reduction from dominating set to the weighted circuit SAT problem, and there the Weft was 2, and therefore you have membership.
We didn't prove that this cannot be done in Weft 1, right? We didn't prove.
No, we didn't prove that it cannot be done in Weft 1. Okay, and we don't know again unconditionally that it cannot be done in Weft 1. But there is, I think, a theorem which says that if it can be done in Weft 1, then something bad happens. Okay. I don't think we can say that P equals NP, but we can say something pretty drastic anyway. So, yeah. Okay. So there it is believed that W1 and W2 are strictly separate classes. Okay. But one thing that's a nice exercise is to show that W1 is contained in W2. Okay. That's not even a nice exercise. It's very trivial. Sorry. What is a nice exercise is that you can play around with the constant 2 and define it with any other constant and it will still work. Okay, but yeah, I mean, clearly W1 is contained in W2. I hope that's clear. Okay, so anyway, by some complicated means, again, you can actually show a hardness result. You can show that in fact weighted circuit SAT reduces to all of these guys. Okay, all right. So at least once in any lecture, I get the direction of the reduction wrong. So please listen carefully.
Why do you even need to show that it doesn't suffice? I mean, it cannot be done with 1, because if dominating set could be done with by Weft 1, then everybody, because it isn't hard for this class. So if dominating set can be done with Weft 1, then everybody here can be done for Weft 1, and then the classes will collapse, right?
The classes will collapse.
They will coincide. Right?
Correct. So if you are happy, for example, if NP collapses to P, then it's the same sort of thing that's happening.
I mean, it's not a worth exercise to try to prove that.
No, we would like to say that, I mean, we would like to say, okay, so one way of saying it is that dominating set is harder than independent set, and therefore if you collapse, then dominating set at least becomes as easy as independent set, and that's a good thing. The other way, right?
Yeah, but if dominating set becomes as easy as independent set, then entire class W2 will collapse to W2.
Exactly. So, and you're saying that that's nothing to worry about because dominating set only becomes easier, right?
That's a matter of
I mean, yeah, I mean, exactly. I mean, I'm just trying to get the, yeah, I'm just asking for the feeling of your question. I mean, are you trying to say that it's okay if they collapse? Or?
What I'm saying is, as long as you go by the conjecture that W1 and W2 are separate classes,
Yeah.
why do you want to prove that?
No, I mean, no. I mean, I'm just saying that is a conjecture. So he was asking if you have shown that W1 and W2 are separate.
Oh.
Yeah. So you're saying that have you shown, for example, that dominating set cannot be expressed by a circuit of Weft 1? So I was just saying that we have not shown that it cannot be expressed by a circuit of Weft 1, but it's widely believed that you don't expect it to be described by a circuit of Weft 1. So either you think of it as dominating set becoming as easy as independent set, or you see it as independent set becoming as hard as dominating set. So depending on which way you're looking at it, a collapse is a good thing or a bad thing, but it's not expected either way. Okay. So so that's the class W2. We will not be able to show again this reduction because this is tough. So these are the two big black boxes that the weighted circuit SAT problem actually reduces to these natural problems. We are not going to go into that, but I'll introduce another black box which will make at least some sort of hardness easy to see. And the black box is also interesting because it ties circuits in with satisfiability. Circuits tie in with satisfiability in a very natural way, but we've been looking at specific kinds of satisfiability, and it turns out that we can actually make certain connections. So if you stare at the independent set circuit again, okay, you'll see, okay, so these were OR gates, and that's actually going to be kind of important. So we had OR gates of degree 2. Okay. So the general structure of this circuit, I mean, it's a fairly simple structure, right? It's not a very ugly, complicated circuit. The generic structure of the circuit seems to be that you have some gates, some of which potentially are negated. In that example, everything was negated, but never mind. So you have some variables that can either stay or be negated, and then they can participate in constraints of length 2, in OR constraints of length 2, okay? And then all of these constraints have to be satisfied together, okay? Does that sound familiar? Question mark. Yeah, that sounds a lot like 2CNF, right? This circuit is in fact describing a 2CNF formula, okay? Because you have OR constraints of length 2, and then all of them have to be satisfied simultaneously, so that's exactly the CNF format, okay? So it's easy to see that, you know, independence set can be described as, you know, weighted satisfiability for just 2 CNF formulas, right? Because you just take every edge and do X bar or Y bar. That's exactly what the circuit is doing, right? In the independence set example, yes. But I'm just saying, in general, you can talk about circuits that have this simple structure, right? It turns out that even if you restrict yourself, okay, I mean, before we go there, let's look at dominating set. The general form of this circuit is that you have a bunch of OR gates, but now they're unbounded. They're no longer constraints of length 2, they're unbounded. They can see any number of variables, and then you have to AND all of them. And this is a lot like unbounded CNF, right? You have clauses of arbitrary length, and then they all have to be satisfied. Okay, so the circuit that represents dominating set is looking like unbounded length CNF set. Okay, and in a surprising result, I think, Downey Fellows showed that you can actually reduce the general circuit set problem, meaning that you give me a circuit that looks as complicated and as ugly as you like, has no form or structure whatsoever, or no evident form or structure. Clearly, this problem reduces to this problem because this is just a special case. What's this problem? I'm saying circuits that look nice, circuits that look like the circuits for dominating sets. So these are, I mean, I don't want to formally define it, but normalized circuits are essentially circuits where you have this very special structure, okay? 2 layers, and in fact, you can even assume that all the variables have the same form. They're all monotone or they're all anti-monotone, like Fahad was pointing out. So even with all those restrictions, okay, you get certain kinds of circuits. These are your circuits that correspond to CNF SAT in some sense. So these special circuits are clearly a special instance of this problem, but it turns out that you can take an arbitrary circuit with no form, shape, size whatsoever, and you can mold it into a circuit that has precisely this shape. Okay, this is again a pretty heavy reduction. You have to do a lot of magic to, you know, and I hope that you think of it as a fascinating result. It's really quite amazing that you can take a random DAG and bring it down to this form via FPT reduction. Okay, but now if you assume this reduction, then it's easy to see that dominating set, etc., actually are hard. So if you assume that this is your canonical hard problem, which people do for practical reasons, then it's easy to see that these guys are hard. So that reduction is a 2-minute reduction. So let's say you start with an unbounded length, unbounded clause length CNF formula, and you're asking the weighted satisfiability question. Can you set exactly k variables to 1 to satisfy this formula? Okay, starting from here, I claim you can go to dominating set, for example. How? Mm-hmm. Good. Have a vertex for every clause, yeah, and then have a vertex corresponding to every variable and draw the incidence edges. Okay, it's very easy to see that if you have k vertices that dominate, then you can use the k vertices to satisfy. I'm starting with a monotone formula, by the way, because even monotone formulas are hard for weighted satisfiability. So starting with a monotone formula, meaning none of the variables are negated. You start with a variable, so the dominating set may pick some clause vertices and some variable vertices, but it doesn't matter. The dominating set is of size k. If it's picking some clause vertices, just arbitrarily choose some variable from it. In the forward direction, if you have a satisfying assignment, pick the variables that were set to 1, they will dominate everybody. If you have a dominating set in the reverse, if it comes from here, great, that's a natural assignment. If some of the dominating set vertices are from the clause vertices, from those clauses, just pick an arbitrary variable to satisfy those clauses. Okay, it won't hurt. Your budget is intact and so forth. Okay. All right, so hopefully that's, that it was a very brief but hopefully a sensible introduction to the W hierarchy. Sorry.
Exactly.
You need to dominate the variables.
Oh, right, okay, I forgot. You can either have a global guard vertex or you can make these guys a clique, sorry. Yeah. You can, so you need to dominate vertices on this side as well, so I forgot. But given all the guarding and the gadgeting we had last time, that's easy to take care of. Okay. Yeah, thanks. So okay, so good. We have that dominating set is hard. From dominating set, you can go to hitting set, you can go to set cover, and all of these problems very easily. And that's hopefully in the problem sheet. Let's just do one more example of a concrete reduction, and we'll be done. Especially since Saket was talking about chromatic number parameterized by tree width in the previous lecture. There is a closely related problem called list coloring, which is like chromatic number, but so every vertex has a list of colors given to it. Okay, so you have to still color the vertices so that every edge, no edge is monochromatic. So you still have to get a proper coloring, but now with the additional constraint that every vertex has to get a color from its list. Cannot just get some random color. Okay. Now this problem parameterized by tree width alone turns out to be as hard as, I don't know, I think as hard as clique or something like this. So let's do this. I think as hard as independence set. Okay. Clique or independence? How does it matter? Yeah. Yeah, let's do multicolored independence set. Okay, so first of all, think about what happens to the dynamic programming when you try to do it for list coloring. All right, it's a natural question. You had, I think, a T power T algorithm where T was the tree width for coming up with the optimal chromatic number. If you want to come up with the optimal list chromatic number, if that's what you want to call it, just run that algorithm in your head and try to analyze the time complexity. Obviously, you have to keep track of a few more things because you are now in a different problem, in a different setting. You have to worry about a list of colors that you have to preserve and so forth. But for now, let's just see a reduction from multicolored independent set. This is a problem that we are hopefully very familiar with. So you're given a graph with k paths, and the question is, can you pick one vertex from each path so that they're independent? Okay. So now we have two things to do. Notice that the parameter here is no longer the solution size. So this is also something that's slightly unusual about this reduction as compared to the ones we saw last time. It was easy to keep track of what was going on in the last lecture intuitively because solution was going to solution and that was your parameter. So things were somewhat natural. Here you have to go from this guy to a graph where the tree width is bounded in terms of k, and a graph which has a valid list coloring if and only if this guy has an independent set, a multicolored independent set of size k. Okay, so any thoughts? What do we want? We want to somehow use the coloring to come back to an independent set, right? And now remember that it's, just a coloring instance will not work. You really have to use the lists because that's what's bringing in the difference in complexity. So what would you do with, okay, so let's maybe just start by saying that suppose I want to just say that here are k vertices, okay, and the vertex vi, or whatever, let's say that this is the vertex maybe wi. I want the colors that these vertices get. This is w1. So I want to somehow say that these vertices should get the colors that correspond to the independent set vertices. So what should my space of colors be? So notice that you have a set of colors as a part of input, and it's not constrained by k. The colors can come from anywhere. So what would be useful colors to use? The parameter is tree width. I didn't write that down. Parameterized by tree width, yeah. You're allowed to generate whatever lists you like. Okay, I didn't really describe the problem properly maybe. So you have a graph and you have a space, you have a set of colors. This is the instance to the problem. You have a graph and a set of colors. Each vertex gets a subset of these colors as sort of a constraint, saying that you're allowed to color this vertex only from its list. So every vertex gets a set L of V, okay, that's a subset of colors, and you're allowed to color this vertex using only colors from L of V, nowhere else. Okay, and this coloring that you generate must be a proper coloring. Okay, that's the problem. Okay, so notice that the additional freedom here is really in the space of colors, and that's what keeps you from getting a good algorithm if you try to think about the DP over the 3D compositions. Okay, because it's an unbounded space of colors. So notice that you proved something about the chromatic number of bounded tree width graphs. Okay. And try to convince yourself that that sort of argument may not work here, because now you cannot do any coloring that you like. Now the coloring is constrained to respect these lists, which can be arbitrary. For example, I can give you, let's say, I don't know, a complete graph, and for every vertex, okay, a complete graph doesn't have bounded tree width, but okay, I can give you maybe a graph that's completely independent, clearly has bounded tree width, and every vertex has a list of size 1 with a different color in it. So the only way you can color it is using n colors. Okay, so even though this graph has bounded tree width, it doesn't have its list chromatic number is unbounded. Think about it, because we're getting late for lunch. Sorry. So, and everyone's hungry and staring at me and so forth. So. Okay, so no, think about it. Basically, the basic premise there is somehow the set of colors you have to deal with is bounded, and that's why you can do something in a bounded fashion. Here, that premise is gone, so you can still get some algorithm. You can get an n to the tree width algorithm, but getting a tree width to the tree width is difficult. Okay, so okay, fine. So somehow I have k vertices in my reduced instance. Let's say this is my starting point, and I want the colors that these guys get to give me a hint about the independent set there. So what's a natural space of colors for me to use? 1 to k, or even a little bit more. I can use as many colors as I want, and the color that I assign to wi, I want this color to tell me which vertex should I pick from vi. But if I just have 1 to k, then that doesn't tell me about which particular vertex I should pick. Nk, I mean even just n, right? If my colors is just, let's say my color set is v1 to vn, where v1 to vn is the original set of vertices. Okay, so then I'm allowed to set wi to one of these vertices. The colors correspond to the vertices. So if wi gets the color vi, that means from the part vi, go and pick the vertex little vi. Okay, so suppose wi gets colored with v3, it means that go and pick v3 in your independent set. Okay, but I have to get a multicolored independent set. So what should I do? What should I do to ensure that wi only gets colors from vertices in the part vi? Okay, this is easy, guys. Are you like really hungry or? Use the list, right? So the list of wi is exactly capital Vi. This will ensure that the color that Wi gets corresponds to a vertex from the part Vi. Okay. So, what you go back to is multicolored, but there is no reason so far that it should be independent. Okay. So, how do you encode the independence? Whenever you have an edge, you would like to have some sort of a violation. So, what should happen? Suppose Wi gets the color V5 and Wj gets the color V24, okay, and V5 and V24 was an edge. Okay. So, I should somehow say that this coloring is bad, okay, for which I need to do a little more gadgeting. So, let us say I introduce a vertex. This is like an edge guard vertex, okay, which says that this for this particular edge. So, this is a vertex x 5, 24, which is, let us say, adjacent to Wi and Wj, and this vertex should get into trouble if these guys get these colors. So, what should I do? Put its list as? Yep, put these two colors in its list. Okay, what happens then? You have to give this guy one of these two colors, but you can't because it won't be a proper coloring. Okay. So, whatever coloring you give here will correspond to a multicolored independent set there. And are we done? Forward direction also goes through. I mean, if you have a multicolored independent set, just color accordingly. Okay. And for each guy here, at least one of these two colors will be free, because if you used up both the colors, then you didn't start with an independent set. So, at least one of these colors will be free, and you can just assign this color. Okay. Are we done? Okay, you wish. We still have to show that the tree width of this graph is bounded by a function of k, because that is the parameter. So, why is the tree width bounded by a function of k? The tree width of this graph. So, the claim is that list coloring parameterized by tree width is as hard as independent set parameterized by solution size. So, I have to make sure that the parameter here is bounded as a function of the parameter of the original instance. All right, if you say so. Sure. What does that tell me about the tree width though? But I didn't start with the bounded tree width. I mean, independent set and bounded tree width is not even difficult.
How many edges have you introduced here?
Okay, Saket, did you do bounded vertex covers, bounded tree width?
W1 to Wk is it?
Yeah. No, just asking.
What is the tree width of a graph on k vertex?
Okay, good question. Okay, exercise, guys. Okay, I mean, you have a huge independent set here. Okay,
Vertex cover, right?
and the top is a vertex cover.
Tree width is one.
Yeah, so the tree width is
Exercise
this
problem.
plus this. Yeah.
First problem.
In the exercise sheet.
Okay, it's there in the exercise sheet. Fine. So you generated a graph whose vertex cover is just k. Its tree width is also k. So fine. Lunch.